okay now? Sasha, do you hear me?
I can't see the slides yet.
Борис Феодорович, мы видим ваш экран, но не видим слайдов. Не открылось. Еще раз откройте лекцию.
Да.
Алло, Борис Тодорович, вас слышно? Только если можно, чуть погромче говорите.
Да, сейчас. Видны ли мои слайды?
Виден ваш экран. Вы сейчас показываете...
Тряхните на слайды. Откройте еще раз, Павел.
Сейчас попробую.
Now it's okay.
Okay.
Все отлично. Сейчас видно все. И вас видно, и видно презентацию. Можно начинать.
Okay.
Спасибо.
So it's a great pleasure for me to meet so many friends and to see in the audience so many young people. But unfortunately, it's in online regime. And I do hope that probably the next year we can repeat this conference and to see each other personally. So let's try to do it next year again. Okay, so my talk today will be about very simple things. It is about two disciplines, optimization and control, how they developed separately at first, how they met, and what are the points of the dating, the results. So sorry for very elementary style of my presentation, but well, sometimes it's useful to speak about very simple things, where they come from and so on. Okay, so I start. Just a moment. Something. Okay, so what is optimization? The brief history of optimization from the very beginning. So it's about minimization of a function, scalar function of n variables, subject to some constraints. And of course, you will see me that there are dozens of extensions, including infinite dimension formulation, matrix variables, multi-objective optimization, and so on. But the main problem is of this sort. So the history started very early. It was optimality condition, the first optimality condition invented by Fermat in 17th century, that the derivative at the minimum point is equals 0. Then Lagrange extended it to equality type constraints. Then just 100 years ago, it was extended to inequality constraints. And also I would like to mention a very famous, not famous, very important paper by Kantarovich of 1940, but unfortunately it's not very well known. It is about general formulation of optimization, exactly in this form, but not in finite dimensional space, but in Banach space, and there were main ingredients of optimization theory there. There was normal cone to the set Q. There was a derivative extension of the derivative to infinite dimensional case, and so on and so on. And there was a general optimality condition. Well, later it was developed a little bit further by the Boris-Newton, the technique how to write this normal cone when Q is the intersection of several sets. But probably the main contribution was due to Kantorovich. Well, then it is one line related to optimality conditions, and another very different line was about methods how to solve optimization problems. And again, it starts with such names as Newton and Cauchy. Actually, Newton never dealt with optimization problems. He worked with solution of equations, but as we know, it's very closely related. Then again, it's another paper by Kantorovich, which is very important. The paper was entitled Functional Analysis in Numerical Methods. And the main idea was that applied mathematics should be considered in the framework of functional analysis. The technique of functional analysis should be the main tool for when we work with applied mathematical problems. And there were two examples there. Steepest descent for minimization and also Newton method for minimization. There are another class of problems for which non-trivial method could be developed. It was simplex method for linear programming. Then I would emphasize the role of Arik Minerovsky, his book by 1976, where it was some breakthrough in optimization, including the idea of complexity of optimization problems, classes of optimization problems, lower bounds, and so on. And then the next very important step was Nestor Minerovsky, it is interior point methods with polynomial complexity. Okay. And also, when working with minimization problems, it was very soon understood the role of convexity and the role of Rickefeller can be overestimated here. And in Soviet Union, it was Boris Pshenichny who introduced the role of, emphasized the role of convexity. Okay. So now turning to control. If first of all there were no theory and there was no this word control, it was something like automatic regulation, and the main words which were used there were like regulator, transfer function, input, output, step response, Laplace transform, stability, Nyquist plot, and so on. And we see there were these keywords do not intersect with similar keywords for optimization. It was absolutely different scientific discipline. Okay. Oh, sorry. Oh. Well, but the 60s, 1960s, there were, sometimes it's called control revolution. It is connected with very simple formulations. First of all, control was formulated as given ordinary differential equation, and in the right-hand side of it, we can change. It's control. X is state variable and U is control. And also, our goal is to optimize something, performance index. So it can be some terminal condition or integral, some integrals, but it doesn't matter. The idea of optimality just it's surprised that it arose so late in control, but it did. Okay. But very soon it was understood that, well, we can look at optimal control as a kind of optimization problem. Let's, for instance, consider control as a function of t. It's so-called open loop control. And then it just infinite dimensional formulation of optimization program. And we can use standard tools of optimization applied to this specific optimization problem in Hilbert space. And then, for instance, we can use gradient method or gradient projection method if we have some constraints for you. And the gradient can be calculated, and conjugate equation is the technique how to calculate the gradient. And there were a series of papers, probably the first was Kelly, 1960, and then Bryson Benham, Lucian Pollack from Berkeley also wrote the book on this connection between optimal control and optimization. And in Soviet Union, I should mention Demyanov, Pshenichny, and also our paper at this meeting in 1966. There was some validation, theoretical validation of these methods applied to optimal control. And also the famous maximum principle of Montraguin, it was understood that it is just optimality condition for this specific optimization problem. And Dubovitsky, Milutin, and later Gersanov explained that it's just a realization of general external condition for abstract optimization problems specified for this kind of problems. Okay. And another direction was in control was due to Richard Bellman, and it was based on Bellman function, and well, maybe this approach was specific for optimal for control. It was not. It's for dynamical systems, not for general optimization problem. But nevertheless, then it was understood that discrete time optimal control. It's just a version of nonlinear programming. And there were books like Tablet and for optimal control by mathematical programming. In the Soviet Union, there was a bunch of authors who were involved in real-life compilations for optimal control. Okay, so now what were some theoretical results? Let's look at the simplest problem of optimal control. When we have linear system, it's linear both in state variables and in control. We have some fixed initial and terminal condition, and we want to minimize quadratic performance index. Then if we, for instance, if we use Bellman approach, the Bellman function could be taken as a quadratic function, and then it leads to explicit solution based on 2-point quadrant differential equation. The important particular case is infinite horizon case, t equals to infinity. Then what is specific here that optimal control can be found in explicit form by Riccati equation. Here it is the quadratic equation for matrices X, and then based on this X we find gain K, and then we find optimal control in this form. But what is the most important that it is not loop control, but it's feedback control. We can take U as we can take U as a feedback linear function of the state, and that's very important because in most real-life problems, nobody will take control as a function of t in advance. Well, we don't know a lot of things. There are some external perturbations, uncertainties, and so on. So we can plan our optimal control in advance, but we can take it as feedback. That theoretical solution for this particular case gives us solution in this feedback form. It's very important. So, okay. Okay, but we can look at this from another point of view. Let's fix the structure of control. Look at it as a feedback where gain k is our variable. Then our equation becomes this one, and now we arrive to the optimization problems for matrices. We are looking for optimal k, such, well, we choose k, we can construct this matrix AK, then we can solve this Lyapunov equation. Variables are now x's, and then we calculate our performance index, and this is exactly a function of k which we minimize. So, well, we arrive to unconstrained optimization problem, and we can solve, say, by gradient method. And actually, this idea was formulated in the pioneering paper by Kalman, and also a little bit later for more general situation by Athens. And calculation of gradient is no problem. Calculation of gradient is no problem here. We just solve an additional Lyapunov equation. But unfortunately, the function we minimize, it is non-convex, and it behaves badly because it tends to infinity on the boundaries of, it is defined only when k is such that AK is Hurwitz matrix, AK is stable, and so we are in stability domain, and so it's constrained optimization, and the function tends to infinity the boundaries of this stability domain, and in general it can be non-convex. So there were a bunch of papers about heuristics here, how to and it was demonstrated that this idea works, but the validation of this approach came just recently. I mentioned here several papers, including our recent paper with my student, Elias Patkulin. And the general result is that, well, our function is the gradients doesn't satisfy Lipschitz conditions on the entire stability domain, but it does satisfy these conditions on sublevel set, and this is very important. We start with some initial approximation, and then we remain in this sublevel set. So, and well, more important was that for some classes of such problems, the problem, our function is gradient dominated. I'll say later in more detail what is it, but it guarantees convergence of the gradient method to global convergence of the gradient method to the unique minimizer. Okay. Now, I said about just the simplest problem of this sort, where our control is the state feedback when we think that state X is available. But in most problems, we don't know X, we have some output Y, which is a linear function of X, and our control should be linear feedback with respect to the output. Okay, then well, there are no disturbances in the formulation here, but it should be considered. And another class of problems where this approach can work, where it's so-called parametric control, something like PID, where our control is has this form, and parameters KI should be found to optimize performance. Okay. And this class of problems, it is it provides some challenges for optimization methods in general. For instance, here, as I mentioned, the function of K is unbounded. So how to design first order methods for minimization? Here we can also calculate the second directional derivative. It's just another Lyapunov equation. Then also, in this case, the stability domain where our function is defined, it's wet, it's non-convex, and it has no explicit description. However, feasibility oracle is very simple. We can immediately check if our controller is stabilizes the systems or not. So how to adjust step size in minimization method in such a way that we remain in this stability domain. Then I mentioned about this gradient diminution property. So it's an interesting question when for this kind of problems we this gradient diminution property holds. And one more comment is, well, in this, for instance, for parametric control, we do this linear with affine matrix expressions like this. It's exactly what we have in LMI, but here AI in general are non-symmetric. And what we need that this set of this set is when this affine combination is ordered. So how it can be deal with such set? This set is when this affine combination is ordered. So how it can be deal with such set? This set is when this affine combination is ordered. So how it can be deal with such set? This set is when this affine combination is ordered. So how it can be deal with such set? This set is when this affine combination is ordered. So how it can be deal with such set? This set is when this affine combination is ordered. So how it can be deal with such set? This set is when this affine combination is ordered. So how it can be deal with such set? This set is when this affine combination is ordered. So how it can be deal with such set? This set is when this affine combination is ordered. So how it can be deal with such set? This set is when this affine combination is ordered. So how it can be deal with such set? This set is when this affine combination is ordered. So how it can be deal with such set? This set is when this affine combination is ordered. So how it can be deal with such set? This set is when this affine combination is ordered. So how it can be deal with such set? This set is when this affine combination is ordered. So how it can be deal with such set? objects. And for instance, there are some funny results here. For instance, if this matrix, the matrices are non-symmetric, but they do commute, then this set is convex. And there are some other classes of problems which are good, but in general, this set is non-convex. Okay. That it's worth analysis. Okay, so now about going back to LMIs and matrix optimization and so on. As I mentioned in the very beginning, the important class of problems was formulated with LMI constraints and SDP semi-definite programming problems with minimization on such sets for convex functions. And then there were introduced self-concordant barriers in imperial point methods and so on. And this is very well developed field now. But what about control? It was very soon understood, and the main role here belongs to Stephen Boyd. That it was understood that LMIs are very important for control programs. And it's based on the fact that if a matrix is Hurwitz, it is Hurwitz if and only if such inequality holds for some positive definite matrix K. And so the problem of stability is reduced to solving LMIs. And then also synthesis problem when we are looking for feedback in this form, and we want to stabilize the system by this feedback. It's also reduced to LMIs. And well, this is a famous change of variables here. We have new variable, matrix variable y here, and then if p and y are solutions of these LMIs, then k of this form is stabilizing controller for linear system. It's very important thing. And now more or less all control problems of analysis, stabilization, design, performance, they can be reduced to SDP. And for instance, if you look at any journal on control, probably you discover that about a half of papers deal with LMI. So it's a mainstream in control. Okay. Now let's sorry. but it was mainly about linear systems. But let me remind the classical results of Lyapunov about nonlinear systems. So we deal with the simplest stationary equation with fixed initial condition. So roughly speaking, the theory is Lyapunov theory is based on the notion of Lyapunov function, such that it is has a single minimum point at 0, and if the derivative of this Lyapunov function on the solutions of these equations is negative, then the solutions of these equations with this initial converge to 0. Okay, very good. And this is so-called absolute stability notion. And if we do it for linear system, so it's without any control, it's just analysis. And then if we take quadratic Lyapunov function, then we get exactly the condition I was mentioning above. Okay, so let's look at it again from optimization point of view. And let's compare optimization and this analysis of asymptotic stability by Lyapunov. So what we have in optimization, we have a function which we, for instance, constraint minimization. Then we construct some method, say gradient method, in continuous time for simplicity. And the problem is to prove this method converges. In asymptotic stability analysis, we have a reversed problem. We have equation, and we want to construct Lyapunov function which is Lyapunov function for this problem. So if we compare these two problems, optimization and stability analysis, so here given function and here given equation, we design a method for minimization, and here we find the Lyapunov function. So you see, this is very closely related problems. Okay, and to get some more or less effective results, we should slightly modify the simplest Lyapunov theorem, and roughly speaking, I will not go into details, but we have this differential equation here. Then we construct Lyapunov function, and we have not its derivative, but some estimate for its derivative with each non-negative. And we can guarantee, without any assumption on V, we can guarantee something about this derivative. Then for convex case, we can specify this theorem, under more restricted condition, we can prove something about V, not only W. Okay, so well, let's look how it works, this technique, how this general Lyapunov theorem works for optimization. For instance, we deal with this gradient method in continuous time for. Then the only condition is that the function, our function is differentiable and it's bounded from below. And then we prove that under this very general conditions we get convergence of gradient to zero, and we have some convergence rate for. Then if we have this gradient domination condition, so sometimes, sometimes it's called Poляk-Lajosevich condition, then we can guarantee convergence and exponential convergence in function. And what is important, so how it works, we have Lyapunov function f, and this estimate W is quadratic norm of the gradient, and then we get this result justifying that theorem. There's no assumptions on convexity, on uniqueness of minimum point. Okay, the next result is for convex case, and for strongly convex case. Well, it's not the best result, but it is just to demonstrate that the technique which is traditional for control for absolute stability analysis, it works immediately in analysis of optimization algorithms. And another example is favorable method, when we introduce inertia or momentum in our differential equation. Again, I consider it in continuous time case. So, well, how can we prove some results about convergence here? Well, first we rewrite our second order system in first order form. Then follow tradition. Well, actually, what is this? It is indeed movement of a heavy ball under with some potential relief. And traditionally, in mechanics, they take full energy as Lyapunov function. Well, there are some difficulties here because our derivatives, it's not negative, but it's not positive. In general, when y is equal 0, it's also 0. We can apply so-called Lassard invariance principle in this case to validate conversion. But well, it's but better to work in different way. Let's change the Lyapunov function. It's not something like full energy. Now it's some combination of potential energy, it is kinematic energy, and some mixed term of this form. Then everything works. And for variable method, we immediately get convergence, and some rate of convergence. Actually, it's bad rate of convergence, but nevertheless, our assumptions are too general. We don't assume the convexity, nothing. Okay. And of course, for convex case, we can also get some results. But what is important that now there are dozens and dozens of papers in this direction. For instance, very promising thing is to introduce not stationary damping, but non-stationary, and to use dependence on T in correct way, and then we can guarantee the right rate of convergence. And for instance, I can mention the paper that I conversed, and there were later many papers that push so on and so on. Of course, it was about continuous time, but we can also do this more important for the calculations, discrete time versions, and so on. And also, it is just examples that this Lyapunov analysis technique works for optimization methods, but also there are another applications of control tools, such, for instance, there is such tool as linear quadratic constraints. They are used to develop other accelerating methods for optimization. And well, now there are these ideas about close connections between optimization and control. It's now very common. And it is just the titles of several papers published in this year, 2021. For instance, you see optimization with momentum, dynamical control theoretic and symplectic perspective, or something like dynamical view on optimization algorithms. Lyapunov analysis of accelerated methods in optimization. You see all this bunch of research is about joint approach to control and optimization. And now there are new trends. Well, I spoke just about controller optimization, but now there are other actors here. And, first of all, this is learning. And now there are new keywords such as policy optimization, adaptive control, and model free control, and so on. So it's the union of three disciplines, control, optimization, and learning. And for instance, the last IFAC Congress, there were there were very few planners there, but two of them were here on the titles. You say the first is learning to control Renaissance, more important learning for process control and beyond. So this is direction is much broader now. There are many conference workshops here, and I cannot get into details here, but just I would like to say that well, the number of points where optimization needs control and some other actors are growing. So, okay, thank you. Let me stop here. Thank you.
Thank you, Boris Todorovich. Please ask your questions, colleagues from Zoom. Maybe you have questions.
I just have a remark. It would be nice to have the Russian viewpoint on the history of optimization as you sketch in the beginning. Because sometimes for us it's not easy since some papers are in Russian and we cannot understand what's in it. So just saying, it would be very interesting because we have mostly the American viewpoint, and I think the Russian one would be very interesting.
Yeah, maybe it's a little bit bias here to emphasize Russian contribution in this, but maybe just, well, if I would write something like a survey, of course, I give much more broader list of works on this, and of course, the contribution of the West should be strong and large. But yeah, for instance, I wanted to mention some Russian guys which are not very well known at the West, for instance, Pshenichny, Shor, some others, Kantarovich, by the way, is much better known, but nevertheless, his contribution is not very well understood. Everybody knows that he invented linear programming. Was one of the inventors of, but his main contribution to optimization was different. It's not so. Thank you for your comment. But of course, I have in my own mind much more objective view on this process. So thank you.
Thank you, Boris.
Thank you. Thank you. Please, more questions? Maybe we have questions from this room. Yes, Roland, please.
Could you go back, please, to the slide with the open questions?
It's channel okay. Oh, this one.
Yes. So the second point, here you have a set S, which has a good oracle. So it means you can detect whether the point is an S or not. But this is a quite weak feature. So there are examples of NP-hard problems which can be formulated as optimization over some set where you have an oracle, but nevertheless it's hard. So what in this case lets you think that one can do some progress here?
I guess that some progress here is to detect some situations which are not that bad as NP-hard. For instance, I mentioned this simple case when matrices are pairwise commuting, and then everything is okay. And it is, you see, it is a little bit different from elements. They are non-symmetric, but they are commuting. So it is, well, it's a simple case, but nevertheless, there are some classes of problems where we can work with this in some effective way.
Okay, thank you. Are there other questions?
Thank you. Please, more questions? So, there is no questions. Let's thank the speaker again. Борис Тодорович, спасибо большое. Спасибо. And we move